In this video, we're going to look at nuclear stability and the types of nuclear decay that can occur. This figure shows the number of neutrons as a function of the number of protons for a series of nuclides. Notice that in this figure, the stable nuclides are designated in black. So the largest stable element would be lead-206. That's lead. It has 82 protons and a mass number of 206. This figure also indicates that there are several nuclear reactions that a nucleus can undergo to transition from being an unstable isotope to being stable. So moving from one of the blue, orange, red, yellow, or green regions and moving into the black region, known as the belt of stability. Nuclides that appear above and to the left of the belt of stability have too high of a neutron to proton ratio. To become stable, they must undergo some process that decreases their neutron to proton ratio. An example of that is beta particle emission. Nuclides below and to the right of the belt of stability have too low of a neutron to proton ratio and therefore must undergo a process that increases that neutron to proton ratio to get to the belt of stability. The examples of that type of process would be positron emission or electron capture. The first type of nuclear reaction that we're going to look at is beta particle emission. In beta particle emission, a neutron is transformed into a proton and an electron. So the beta particle, the electron, is getting emitted from the nucleus where the proton stays. Here's an example where potassium-40 is transformed into calcium-40 and an electron is emitted. Notice that the neutron to proton ratio went from 1.105 to 1.0 as a result of beta particle emission. Next, we will look at positron emission. In positron emission, a proton is converted into a neutron and a positron. So the positron is getting emitted from the nucleus. As an example, we have potassium-38 is transformed into argon-38 and a positron is emitted. Here, we start with a neutron to proton ratio of 1 and the proton to neutron ratio changes in the argon-38 to 1.11. Therefore, we've increased the neutron to proton ratio. The final example of a nuclear reaction that we'll look at in this video is electron capture. In electron capture, a proton reacts with an electron and those two particles are transformed into a neutron. This typically happens with a 1s electron, so a core electron that's very close to the nucleus. For an example, we have iron-55 reacts with an electron and is transformed into manganese-55. The neutron to proton ratio was 1.115. After the reaction occurs, the new neutron to proton ratio is 1.2.